Right, welcome back, everybody. Today we're going to be doing section 6.5. I'm really excited about this section because this is when we finally get to see the graphs of these trigonometric functions that we've been studying since section 6.3. It's just really cool. The geometry here is amazing. We're going to get to see why these things relate to waves and oscillatory behavior. It's just super cool. Okay, let me pull up the slides and let's roll. All right. Oh yeah, so this section's all about the graphs. Let's look at an overview. I'm going to give a little bit of an introduction here. Then we're going to recall the big picture again. That shows up over and over and over again. Remember, that big picture is the one that you want to have memorized. It's going to show up forever. All right, make sure you know that big picture. Then we're going to look at the graph of y equals sine of x. We're going to look at the graph of y equals cosine of x. Then we're going to take a look at a few important animations. I feel like these animations just really hammer home exactly why the graphs of these functions look the way they do. And I think it'll really show you why these things are related to waves and wave patterns and so on. Then we're going to look at the graph of tangent of x. Then we're going to talk about an important property of limits. This property is actually really helpful, and you'll see it again in Calc 1, Calc 2, Calc 3 just forever. But this important property of limits is going to make graphing the reciprocal functions really straightforward. And that's why I like to not only talk about this property of limits, but to give you some exposure to limits earlier on in the course, so that when you get to this, you're like, oh yeah, that makes sense. Okay. Oh yeah, then we're going to talk about the reciprocal graphs, cotangent, cosecant, and secant. All right. Okay, so let's roll here. We're going to graph the six trigonometric functions in the xy plane. And like I had said a minute ago, I guess I kind of jumped the gun on that one. This is going to reveal the oscillatory and the wave patterns that are innate to these functions that make them so fundamental to math and science. Yeah, in essence, these functions and combinations of these functions allow us to encode oscillatory behavior in a really robust way. So if you want to study anything that involves waves at all, you're going to use sines and cosines. You're going to use trigonometry. That's why it's such a powerful subject. It's such an important field of math. It gets used anywhere, and I mean that literally anywhere you want to study wave patterns, whether it be microwaves, radio waves, ocean waves, any kind of waves. If you want to talk about string theory, it all uses these basics of trigonometry, sines, cosines, and the graphs that you're going to see today, and in the next section when we talk about transformations of these graphs. So one thing I got to say here, a little note about this. Because we're going to be plotting these things on the XY plane, X is going to be the symbol representing the input of our functions, all right? And Y is going to be the symbol representing the output. So just go back to what we talked about way back in chapter 2 and graphing and all that stuff. That's all the same, okay? So because of that, we're going to write our functions like so. So y equals f of x, which is sine of x instead of theta, cosine x, tangent x, cosecant x, secant x, cotangent x. That's all. The inputs are going to be on the x-axis, and the outputs are going to be on the y-axis. That's all I'm trying to say here. Um, yeah, and like we've seen a bunch of times now, the best way to make sense of what these graphs look like and where they come from, how they're produced, is to remember the big picture and imagine the unit circle. So just to refresh your memory, here's the big picture again. Hopefully by now you're like, okay, I got it, I got it. I dream about this picture when I fall asleep. That's great. You're in a good place then. Just to refresh your memory, as this point moves around the circle, the vertical displacement is given by sine of theta. The horizontal displacement is given by cosine of theta. But the idea is that the circle just keeps moving around and around and around, right? And so what's going to happen is the horizontal behavior is going to go back and forth, and the vertical behavior is going to go back, I'm sorry, up and down and up and down. That's what we're going to try to plot on the XY plane. Um, uh, yeah. So how are we going to do this? Well, we're going to start by using the definition of sine and cosine, which I just said. And the good news is that those standard angles that you've memorized, right? You've got those memorized. those are going to give us key points on the graph. So we can use those standard angles and the values of sine and cosine at those standard angles to plot points that'll give us kind of a skeleton of the graph. All right. Or yeah, they'll be like anchors. The other good news is sine and cosine are 2 pi periodic. They repeat every 2 pi radians, right? We love periodic functions because then we only need to graph one period of the function and we can just copy the graph that we see on that interval, or I'm sorry, on further intervals of the same length. So these functions are 2 pi periodic because as you go around the unit circle, the horizontal and vertical displacement will repeat because that point is going to go back to the same spot over and over and over again. So we're just going to focus on graphing one period. And then what we can do is we could just repeat that period if we want the full graph. Because remember, these functions are defined on all real numbers. So sine of x, cosine of x, the graph is, over the entire x axis, right? All real numbers are allowed, but we only need to graph one period on the interval from 0 to 2 pi, and then we can just repeat that graph as we go forward. So let's start with sine. Sine of theta is usually the best place to start. Remember that sine is the vertical displacement of this point, like I just mentioned. And as the point moves around the circle like so, the vertical displacement is going to go up and then down and then up and then down and so on, with the location of the point repeating every 2 pi radians, right? Repeating every 2 pi radians. So we can plot the behavior on the xy plane and produce this graph right here. Okay, so this is a graph of y equals sine of x. Again, the angle that we're putting in is being plotted on the x-axis. So these are angles that you see right here. 0, pi over 2, pi, 3 pi over 2, 2 pi. And if we remember what the value of the sine function is at those angles, we will get these key points right here, right here, right here. And then we're going to connect those points with a smooth, continuous curve like so. Oh, maybe I'll add this right now for the first time. You want to practice getting good at drawing these sketches. Um, they're not linear functions. These are not linear functions, so you shouldn't be going eh, eh, they shouldn't be like cornered, right? So it's a nice smooth wave connecting all those points. So it's good to practice that because you'll have to draw them a lot in this class, and then in Calc 1, and then in Calc 2, and in Calc 3, you'll be drawing these graphs a lot. But this is what it is. So remember when the angle is 0, sine of 0 is 0 because there's no vertical displacement. So we have this point at 0, 0. Then at pi over 2, sine reaches its maximum. It's equal to 1. The vertical displacement is 1. So we have this point, pi over 2 comma 1. Then when you go around the circle, right, imagine the unit circle. When you're at the angle pi, vertical displacement is 0 again. So you're down here on the x-axis when y equals 0. Then as you continue around and you go to 3 pi over 2, that's when sine is going to be at its minimum, -1. So we're down here at -1. And then it swoops back up, right? Imagine the unit circle, you swoop back up. And when you're at 2 pi, the vertical displacement is 0 again. So you get 0. And this is what the sine curve looks like. Okay, talk about some details here. You can extend the graph in either direction. So this was one period of the sine function, but you could also extend it back this way. And it will keep going. It'll keep going forever in both directions because the domain is all real numbers, right? The other thing you can see is you can see that the graph of sine is symmetric about the origin, right? Take a look at that anchor center right there. The graph looks like that. The graph looks like that. You can see the graph is symmetric about the origin. What does it mean if a graph is symmetric about the origin? It means that function is an odd function. So in particular, sine is an odd function, which means that sine of negative x equals negative sine of x. Let me show you visually here. Here. Maybe I'll do this. Okay. If pi over 2 is the angle we put in, Wait, sorry, maybe I'll start with this. If negative pi over 2 is the angle we put in, we get -1, right? If pi over 2 is the angle we put in, we get +1. So that's why we're getting -1, which is +1. Maybe that was more confusing, but that's the idea. Changing the sign of the input changes the sign of the output. That's it. So if I went from pi over 2 to negative pi over 2 as inputs, I'm going to go from 1 to negative 1 as an output. That's the idea. Or maybe more precisely, or maybe as another example, sine of negative pi over 4, which is right here, right, is going to be negative sine of pi over 4, which is negative root 2 over 2, because sine of pi over 4 is going to be right about there, root 2 over 2. That's it. That's just kind of a geometric argument. We are actually going to prove this algebraically in section 6.8. Actually, algebro-geometrically, I should say, because we will use a geometric argument as well, but we're going to use the definition of sine. So that kind of works out that way. Okay, now let's talk about the graph of cosine. This is the graph of cosine. And again, how do you actually plot this? You imagine the unit circle, think about what the horizontal displacement is going to be at a different at any given angle, and then you mark those key points. We have our standard angles, these quadrantal angles, 0, pi over 2, pi, 3 pi over 2, 2 pi. You can always use more intermediate angles. You could use pi over 4, which is right between 0 and pi over 2. It's half of pi over 2. You could use 3 pi over 4. You can always add more to get more key points to graph. And we actually have several, right? We actually have three other standard angles in each one of these intervals, right? We have the sixths, the thirds, and the fourths. So you could even plot more of these points if you want to. And that'll just make your graph look even more precise, your sketch even more precise. But let's go through why this one looks the way it does. When our angle is 0, imagining the unit circle means that the horizontal displacement is at its maximum. It's at 1. So we have this point 0, comma 1, 0, comma 1, right? Then as that point moves around the circle, when it gets to pi over 2, the horizontal displacement is 0. And that's why we're down here at 0. Excuse me, down here at 0. Then imagining the unit circle as we continue past that point, the horizontal displacement goes this way. Now it's negative, so that's why we're dipping down and below the x-axis. And it's going to go all the way down until cosine is at its minimum, which is negative 1. Oops, come back. There we go. Which is negative 1, like so. Okay, imagining the unit circle. Imagining the unit circle. Okay, now we're here. We're going to keep going. The horizontal displacement is going to decrease to 0 again. That's why this graph curves up. So you're on the y-axis when y equals, I'm sorry, the x-axis when y equals 0. And then continuing even further, now the horizontal displacement is going to be positive until it goes back up to 1. And that's how you get that graph. Just like that. Practice that swoopiness. There you go. Practice that swoopiness. You don't want to go, That's not the cosine graph. Yeah, this is not the cosine graph. That's like the absolute value graph, right? This one is swoopier. Swoopier. Okay. Now, we can extend it in both directions. So this is one period that we just looked at. But again, it keeps going on forever in both directions, just like so. It's defined on R, so we're allowed to do that. Now we can actually see that this graph is symmetric about the y-axis. Check that out, right? You see that? So this side looks the same as this side. There's a reflection through the y-axis. Remember, what does it mean for the graph to be symmetric about the y-axis? That means the function is an even function, right? So cosine is an even function. And what that means is changing the sign of the input does not change the sign of the output. So here at pi, I get negative 1. But at negative pi, I also get negative 1, right? There you go. So no change. Changing the sign of the input doesn't change the sign of the output. Here's an explicit example. Cosine of negative pi over 4. Negative pi over 4 is right here. Cosine of this value is the same as cosine of pi over 4. Right there, you have the same output value. Root 2 over 2 in this case. And again, we'll prove this in section 6.8. Although, I think I might save that for the activity. I might have you do that on the activity instead. It's fun to explore these things and discover them on your own for the first time. Now, a little note. One thing you might notice about this graph here and this graph, this is sine, this is cosine, sine, cosine, sine, cosine. You might notice that the graphs are very similar, right? There's a reason for that, and that has to do with that co-behavior of those two functions. In particular, the sine and cosine graphs are just shifts of one another. And that's because they're co-functions. So the graph of sine is basically a shift by pi over 2 of the cosine function. So if this is the cosine function in blue, sine is that same graph, but you shift it to the right by pi over 2. That's it. So you take the cosine graph, you shift it by pi over 2 to the right, and you get the sine graph. That's the basic idea, which is kind of nice because that means, in a sense, depending on what application you're using, it doesn't really matter which of these two functions you use. You just got to remember that they could differ by what's called a phase shift. This is called a phase shift. And I'll explain more about what that is in the next section when we look at transformations of these graphs. Okay, now we've kind of seen what these graphs look like, but now what we need to do is we need to take a look at some important animations. I only have a couple here that I'm going to show you. There are many really, really cool animations that explain what's going on with trigonometry. I encourage you to look them up online. There are just so many great ones. I have a couple here. So here is the first one I want to show you. And I like this one because this one's going to show you why why these things are related to waves. All right, here we go. Okay, so I want you to stare at this picture for a minute. Just stare at it, zone out on it, look at it, look at what you're witnessing. See that point moving around and around the circle, right? There we go, moving around and around the circle, round and around. Okay, and then I want you to realize that what's happening over here, this is the sine graph. This is the graph of sine of x. And what's happening is this is plotting the vertical displacement of that point as it moves around the circle, right? It goes up, down, up, down, up, down, up, down. So the sine graph looks like this. It looks like this. It's just encoding that vertical up and down displacement, just like that. Up, down, up, down. And now, just turned on its side up here, this is the graph of cosine. It's just drawn like this so that it can line up with that horizontal displacement. But notice it's going back and forth, back and forth, back and forth, back and forth. And this is why these things are related to waves, right? So I don't know about you, but to me, that's mind blowing. Like this picture, man, this animation alone, this is why the graphs look the way they do. This is what cosine and sine are encoding. This is why they are so cool. And again, this is just a unit circle, right? This is a unit circle. We can do all sorts of things to manipulate this graph. We can change the size of the circle. We can make it a different shape instead of a circle. We can, like if we change the radius of the circle, that's going to decrease the height of that wave that you see over here, right? If the circle is smaller, the wave is lower in height. If the point moves faster around that circle, then these waves are going to get closer together, right? This is all coming together from what we talked about before. The faster the point moves, the closer those things are because the period is less, and on and on and on and on. There's just so much. Anyway, mind blowing, mind blowing. Um, here's another one. Here's another animation that kind of shows how these things are traced out, right? So here, yeah, oh yeah, you can see it better on your screen, I think. So yellow is the angle being traced out. It's the angle theta, and they've got it kind of pictured right up here. The red curve is the sine curve. And again, it's just showing you how as that point goes around the circle, the vertical displacement goes up and down, and then up and down. And that's it. What's nice about this animation is they actually mapped the horizontal displacement to a vertical graph. So this is the graph of cosine that we were looking at just a moment ago. That's all they're doing here. Don't worry too much about this, like these like half or quarter circles you see here. They're just trying to show you that they're taking the horizontal displacement, rotating it so that it's graphed vertically, just like we did with the cosine graph. And again, these graphs are they only differ by a shift of 90 degrees or pi over 2 radians, right? It's the same graph. That's it. Okay. So yeah, I encourage you to stare at these graphs, stare at these animations a lot, make sense of them. This is where it all comes from, okay? This is why trigonometry is so cool. All right, all right. Okay, next we got to talk about tangent. So let's go back to the slides for a second here. I've got another animation for tangent to show you, but let's talk about what the graph is going to look like more precisely before we just see an animation of it. So remember that tangent is sine over cosine. It's the ratio of sine and cosine. And it's the slope of the line that passes through the center of a circle and a point on that circle, right? So excuse me, um, that's what we're going to try to plot. Now, remember, the domain of tangent is a little bit different. The domain for sine and cosine was just all real numbers, right? But the issue here is the domain with tangent is not all real numbers because we can't have cosine being equal to 0. So the domain of tangent actually excludes all the odd multiples of pi over 2. This is a picture of the domain of the tangent function, right? So 1 pi over 2, 3 pi over 2, 5 pi over 2, negative 1 pi over 2, negative 3 pi over 2, and so on. All right. Now, thinking a little more analytically here, uh, tangent is a ratio that has no canceling factors, right? There are no equivalent factors in the numerator and the denominator. And what we remember from chapter 3 is that when there are no canceling factors, you're going to end up with a vertical asymptote. So in this case, there's going to be a vertical asymptote at every odd multiple of pi over 2. So the domain excludes those numbers, but graphically, we're going to have a vertical asymptote at every one of those numbers just like that. All right. Yeah, so our graph is going to look roughly like that. Roughly like that. Also remember that the period of tangent is pi. Unlike cosine and sine, the period is pi. And that's just because the slope of that line repeats every pi radians. Wait, did I do that right? Yeah, from here to here. Hold on, am I doing that right? From there to there, those two lines have the same slope, this one and that one. And I only had to rotate 180 degrees. I didn't have to rotate all the way around, right? I just had to go 180 degrees. That's why the period is pi. So the space between these asymptotes is pi in length. That's one period right there, and one period, and one period. So let's see what the graph looks like for just one of these periods. It looks like this. All right, let's try to make sense of what this is showing us. So one, we have these vertical asymptotes, like we just talked about. And remember, this is showing us what the slope of that line will be as that point moves around the unit circle. So imagine the unit circle. Okay, if we're right here, the slope of this line is 0. So when the angle is 0, the slope of the line is 0. So we have that point right there. Now, as our angle twists around, the slope of that line increases, right? So as we go from 0 to pi over 2, these lines increase in slope and they increase until infinity, right? So as our angle goes from 0 to pi over 2, the slope of that line increases and blows up to infinity. And it would be equal to infinity if we were directly overhead vertically, right? So that's why this graph is swooping up asymptotically to infinity as x approaches pi over 2. That's what's going on. So again, just imagine these slopes just like that, okay? Now let's go the other direction. Remember, angles can be negative or positive. So now instead of turning counterclockwise, let's turn clockwise. And as the angle goes down like this, the slopes of the lines are going to also get large in size, but negatively. They're going to go down to negative infinity, right? So here we go. As x goes from 0 to negative pi over 2, the slopes are increasing in size, but negatively in the negative direction, right? One thing I'll point out, these key points right here, those are the diagonals. Those are the diagonal lines. So when our angle is, oops, sorry, when our angle is exactly pi over 4, right? When our angle is exactly pi over 4, the slope of that line is 1. There you go. And when our angle is exactly negative pi over 4, right? Our slope is negative 1. Negative 1. So that's what those key points are. The key points for this graph are occurring at 0, pi over 4, pi over 2, and then the opposites as well, negative pi over 4, negative pi over 2. But that's just one period. So this is what it looks like when you graph it more, when you graph it over several periods or just on the real numbers, right? So the graph repeats. It's periodic, so it repeats. But that means that these asymptotes are going to repeat, and that swoopy graph is going to repeat. And you can go in the negative direction too. And that is the tangent graph. That's the graph of the tangent function. Now, let's take a look at why it looks like that using an animation. Let's get some deep intuition for why. Let me pull it off right here. Hold on one second. Okay, here we go. Okay, yeah, and we're going to watch this a few times. So over here, this is that unit circle. Okay, unit circle. And then you can see that there's this blue line. That's basically the line that we're finding the slope of. When the line is horizontal, the slope is 0. But then as that line rotates around the circle, the slope of that line increases. And then when it gets vertical, that's where that asymptote occurs, right here. But notice that the moment this line gets to the other side of pi over 2, that angle, the slope of the line is now negative. It's going downward. That's why the tangent graph goes up to infinity on the left of pi over 2, and then snaps down here to negative infinity on the other side of pi over 2, and then swoops back up. That's what you're getting. Yeah, that's what you're getting. And then, again, like for me, boom, mind blowing. So just like stare at this figure or stare at this animation, look at it, make sense of it. You can even look up more of these types of animations. There are so many more, but this is why the graphs look the way they do. And I hope you appreciate it because I just think it's super exciting. Okay, I'll stop gushing about it now. Okay, let's get back to the slides. Um, Okay, back to the slides. Where was I? Oh yes, that's right. Tangent graph. The animation of the tangent graph. Oh, I even forgot to go to that slide. I got way too excited there. You can follow that link to find that animation. Okay, so now before we talk about the graphs of the reciprocal functions, I want to talk about an important property of limits. Okay, and that property is given by this proposition. So let's state it, let's talk about it, and then we're going to see it in action. It's a really, really helpful proposition. So for isolated zeros and infinite limit points, if the limit as x goes to a from the left or the right of f of x is equal to plus or minus infinity, then the limit as x goes to a from the left or the right of the reciprocal, 1 over f of x, must be equal to 0. So in other words, this is kind of like the intuition here. If a function has an infinite limit point at a point x equals a, then the reciprocal function has a 0 limit at that point x equals a, has a 0. So what this is saying is by reciprocating the function, it converts zeros to infinities, or it converts infinities to zeros if you reciprocate. Okay? Couple of little notes here. This word isolated. Isolated in this case just means that those zeros or those infinite limit points aren't densely packed. They're not dense in that area, and if they're dense in that area, this may not hold. But we haven't actually seen any situations of that in this class, and you won't see any situations of that in the calculus sequence. You will see situations like that when you get into an upper division math course. So math majors, you will explore this later on in your math education. But for us, all of the zeros and all of the limits that we're dealing with are isolated limits. So the takeaway from this is basically if you've got a vertical asymptote, then the reciprocal function will have a 0 at that point. Yes, that's what it means. If you've got a vertical asymptote, your reciprocal function will have a 0. If you have a 0, your reciprocal function will have a vertical asymptote. That's the basic idea. Um, yeah, another note down here, this is an important bit. Reciprocation doesn't change the sign of a number, right? If I have -2, -1/2 is still negative, right? Like reciprocating -2 to be 1 over -2, that doesn't change the sign of the number, all right? So whatever the sign of your function is, that's going to be the same as the sign of the reciprocal. I'm talking about plus or minus here, okay? We're going to use this to help us graph these things, but let's see it in action once. Let's check out this example for a minute. Suppose we have the function f of x equals 5 over x minus 3 squared. Now, remember from chapter 3, this thing is going to have a vertical asymptote at x equals 3, right? There's basically a hole in the domain there. And because this is squared, the graph is going to look kind of like this, right, when x equals 3. So you've got an infinite limit when x equals 3. So in other words, as x approaches 3 from either side, because of this square, the limit of this function is going to be plus infinity, right? It's going like whoosh, whoosh, right when x equals 3. That's what it looks like. Now let's reciprocate the function. Let's take this and flip it. When we flip it, 1 over f of x is going to look like x minus 3 squared over 5. Okay, now I want you to think about it like this. There's a 0 here. This function 1 over x has a 0 at x equals 3. So this reciprocation turned an infinite limit into a 0. And that's what's happening with that important property of limits. And if you take the limit here as x goes to 3, you can just plug the number in at this point because this function is continuous at x equals 3. You can just plug in the number 3 for x and you'll see that you get a 0, okay? So that's the important property. Let's prove it real quick. The proof is very intuitive. It's straightforward. Here, I'll explain it right now. If the values of f of x grow larger and larger in size as x approaches a, then the denominator of 1 over f of x would grow larger and larger in size as well. But if the denominator of this is growing large, then the value of this is getting smaller and smaller, and it converges to 0. That's basically it. That's basically it. If f of x is getting really, really big, 1 over f of x is getting really, really small, and it will converge to 0. That's why that property works. Okay, now, we're going to see exactly why this property is so handy when we try to graph those reciprocal functions. So let's talk about cotangent first. So remember that cotangent is just the reciprocal of tangent. So it's cosine over sine. The domain is all the real numbers such that x is not equal to an integer multiple of pi. So this is like a picture, right? Of what the domain of cotangent looks like. Can't be pi, can't be 2 pi, can't be 0, can't be negative pi, can't be negative 2 pi. Same deal as before. There are no canceling factors. So at these holes, you're going to have vertical asymptotes. Notice these vertical asymptotes are not at the same place as they were for tangent, right? They are not. That makes sense because of that important property of limits. And what that property says is, hey, everywhere your tangent graph had an asymptote, cotangent is going to have a 0. And everywhere tangent had a 0, cotangent is going to have an asymptote, just like that. That's what it says. And in fact, I think that's exactly what I say here. Yeah, this is exactly what I just said out loud. Yeah, exactly. Everywhere tan has a vertical asymptote, cotangent will have a 0, and everywhere tangent has a 0, cotangent will have a vertical asymptote. Also, remember that the sign will be the same because reciprocation doesn't change the sign of a number. So the sign of cotangent will be the same as the sign of tangent for every x where they're defined. So this tells us if the graph of cotangent lies above or below the x-axis. Let's take a look at it. Here it is. So this is the graph of cotangent, one period of cotangent. The period is still pi, so this distance right here is pi. Actually, maybe I should have like labeled this. This should be 0 right here. This should be, I'm sorry, yeah, wait, hold on. Wait a minute. Pi, yeah, this should be pi. There we go. Yeah, I should have labeled that pi. I'll fix that after the recording. But yeah, again, so one thing I want to point out is this is not just the this is not just the graph of tangent like shifted over a little bit, okay? And it's not just the graph of tangent vertically reflected. So you want to be careful there. Because remember, tangent had an asymptote right here and right here. So tangent actually looks like that. That's not this. So it's not just taking cotangent is not just taking the tangent function and reflecting it across the x-axis. That's not what this is doing, right? Cotangent is reciprocating the function, and reciprocating the function is not just reflecting across the x-axis. That's why what you notice here is everywhere that tangent had a vertical asymptote, cotangent now has a zero by that important property of limits. Everywhere that tangent had a zero, like right here, cotangent now has a vertical asymptote. So that's what's happening. You're reciprocating the function, not just flipping it upside down, okay? So beware of that, beware. And this is what it looks like. Key points, 0, pi over 4, pi over 2, 3 pi over 4, and pi. And then remember the sign, like the plus or minus, is going to be the same as tangent. So remember, tangent was going like this. Maybe I'll still do a quick sketch. Tangent looked like that, and then it came up like that. There we go. Yes, and then it had an asymptote like right there. Okay, so take note of this, right? Tangent is above the x-axis over here. That's why cotangent is also above the x-axis over there. The sign has not changed. Then right here, tangent has a vertical asymptote, so cotangent has a zero. But then after this point, tangent is negative, right? Tangent is the pink. So tangent is negative, and that's why cotangent is also negative. It's below. And then it repeats that behavior forevermore. Here's a graph of cotangent on the whole real line, or at least a snapshot of it on the real line. And that's the basic idea. Okay. All right, now let's talk about the other ones, cosecant and secant. And these ones, man, they might be my favorite, although sine and cosine are just so beautiful. Maybe I like these because they're so closely related to sine and cosine. Um, yeah, we'll see. Funny enough, the rest of these slides, a lot of them are just pictures. I know there's like 35 slides here, but I think about 8 of these slides are just a bunch of pictures to kind of show you the idea. All you need to know to be able to graph cosecant and secant is how to graph sine and cosine. If you can graph sine and cosine, you can graph cosecant and secant. So remember that these are just reciprocals of those functions, right? So we're going to use that important property of limits like before, and we're going to even be able to use that to deduce properties like the domain and the range and things like that. So the easiest way to graph these graphs is to first graph sine or cosine first. So if you're asked to graph cosecant, pretend it's sine first, and then use that important property of limits to get the graph of cosecant. We're going to see that in just a minute here, but yeah, that's what I'm saying right here. Graph the non-reciprocal function, and then use that property to graph the reciprocal function. So here we go. This is the fun part. Okay, this is the graph of sine of x, right? We saw this before, whoosh, okay? This is the graph of both of sine and cosecant of x, which is 1 over sine. Then this is just the graph of cosecant of x. I removed the non-reciprocal function. Let me go back here for just a minute. Check out what's going on here. So everywhere sine has a 0, cosecant has a vertical asymptote. Basically, there's like this midline, right? And every time sine crosses that midline, that is where we're going to have a vertical asymptote for cosecant. There it is. Remember the sine value, like the plus or minus, is the same. So here, sine is above the x-axis, so is cosecant. It's positive. Down here, sine is negative, so is cosecant. It's negative. And now here's the even cooler part, right? Notice these little key points here at these peaks and these troughs. Well, here, the output of sine is 1. What's 1 over 1? It's 1. So the graphs actually intersect at this point because 1 over 1 is equal to 1. And so the cosecant graph actually contacts the sine graph right there. And it just goes like that. So when you're graphing the cosecant function, here's how you're going to do it. Graph sine first. Graph sine, pretend even in the next section when we talk about transformations, pretend this is just sine. Okay? Then you're going to use that important property of limits. You're going to mark all the vertical asymptotes. So everywhere this graph has a 0, its reciprocal will have a vertical asymptote. Here we go. Vertical asymptote right there. Vertical asymptote right there. Ooh, that was bad. Okay, try that again. Okay, here's another one, vertical asymptote. Okay, here's another 0, so I'll have a vertical asymptote when I reciprocate. There's another one, vertical asymptote. Okay, now I'm going to graph cosecant, and it's got to touch each peak and each trough, and it's just going to have that asymptotic behavior. Goes up like that, like that, and like this. Ah, I can do better than that. Come on. And that's the graph of secant, cosecant, sorry. How did I do? Oh, pretty good. It's good for a sketch, right? Nice. Okay. Well, maybe, you know what? This is a great time for you to try something. I haven't had like any examples for you to do in this particular lesson. So we're going to do this. Okay. Try to do this one on your own, okay? Here we go. This is the graph of cosine. From this, I want you to try to graph the graph of secant of x right here on this picture. So think about it for a moment, right? Say something about it, verbalize it. What do you think you're going to do? And then try to sketch it on your own, and I'll do it in just a moment as well. Okay, let's do it. So I'm going to draw my vertical asymptotes first. And I know that everywhere cosine has a 0, secant is going to have a vertical asymptote. So I'm looking here, 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 just like we learned in section chapter 2, right? When we were finding the zeros of functions. It all comes together, vertical asymptote. When I reciprocate, that 0 becomes a vertical asymptote. When I reciprocate, that 0 becomes a vertical asymptote. Okay, now my graph has got to touch each peak and each trough. And now I'm just going to sketch it. So up like that and down. Maybe I'll do this one too, just for completeness. There we go. This one coming down, swooping up. This one going up, swooping down. This one coming down, swooping up. And that's the graph of secant. Let's see how I did. Boom, there it is. Boom, there it is. And this is the graph of secant on its own, secant on its own. So that's basically it. That's pretty much it. That's pretty much it. Last little details about these things, those disconnected pieces of the graph that you saw, those are called branches. This is what I already said a bunch of times. Whenever sine has a 0, cosecant will have a vertical asymptote, and so on. Another thing that's cool about these pictures that I didn't say outright, but I'll go back and show you now. You can see now that the range of cosecant has to be -infinity to -1, and then 1 to infinity. So before we had talked about it, and I had showed you algebraically that that was the case using this result right here, right? But now we can see it graphically. Check this out. Let's go back to cosecant. So this is the sine graph, and this is cosecant, right? Like that. Okay. Well, this is why the range is from 1 and up and -1 and down. So that's why we're getting that range. There's like a big gap in the middle that these functions never achieve because they are reciprocals of those other graphs, of those non-reciprocal functions. So the range very much is from 1 to infinity and from -1 to -infinity. That's why the range of these functions is that way. That's all I'm saying right here. This. There you go. That's equal to that. Okay. And it's the same thing for secant as well. I won't dwell on this anymore. Pretty much just repeating the same thing I said a whole bunch of times. So I won't repeat it, but you can read this if you would like. On that note, it's time to play. All right, let's play. I hope you enjoyed this lesson. It's one of my favorites. It's just really cool. The graphs are so natural. The animations just give so much intuition. It's just amazing. I love this stuff about trigonometry. The next section, we're going to talk about transformations of these graphs, and I'm going to go through a whole bunch of examples about how to do that. That's one of those skills that you really, really do need in Calc 1 and Calc 2 and Calc 3 and a lot of your major courses. So it's worth having a whole section on just how these graphs look under transformations. So I'll save that for the next lesson. Thank you all again for watching, and I will see you next time. Have a good one.